Okay, so we are looking at this situation where we have reaction time in seconds. N is our number of choices. So here's our equation. The window is 1 to 10. And so it looks like this in your calculator. And then we looked at part B and they gave us 7 choices, which is the variable value. We plugged it in and found 0.542 seconds. Okay, so part C, if the reaction time is to be at most 0.5 seconds, how many choices can there be? All right, so what are we given here? Function. So we're given the function value. The function is R, so we have R equals 0.5. Okay, so in our equation up here then, 0.5 will go in place of R. So we'll have 0.5 equals 0.17 plus 0.44 times the log of N. Now, we already have this in our calculator as Y1. So what do we do with this? Y2. There's our Y2. I'm going to leave the same window and go to zoom 0 and see if I get an intersection, and I do, so I'm not gonna have to make any changes to my window. So now if I want that intersection, you need to go to calc. Intersection, which of course is what, 5? And then enter, enter, enter. And then we get X equals 5.623. And we get Y equals 0.5. Okay, so what would you give me? How would you label and show your final answer? So we've done all the work, but what's my answer?
5.62.
And what do I label it? Because it's not X in our original equation.
N.
It's N because this is your variable, right? So N equals 5.623. And at the top of the page, we labeled what variable was, which is what?
Number.
Yeah, so it's 5.623 choices. Explain in practical terms the concavity. Okay, so if we look at our picture, what is that concavity? Concave down. And so we're going to explain in practical terms. So we're explaining the function. And if you look at the very top of the page, we define the function as the reaction time. And now, based upon your graph, what is it doing?
Decreasing.
I don't think it's decreasing.
I mean, increasing.
Increasing at a decreasing rate. All right. Use a formula to express the number of choices as a function. So it wants us to change the number of choices as the function. So here's our equation. R equals 0.17 plus 0.44 log of N. And what it's wanting us to do is it wants us to take this equation and solve for N. Okay, So this one with the log is gonna take a little bit more work. You do need to know how to do it, but you're not gonna see this type of question a lot, okay? So we know an equation, the equal sign is what separates both sides. If I need n by itself, I first need to get this whole term by itself. So the easiest thing and what we need to move first is the 0.17. How will we do that? We're gonna subtract it. So we're gonna subtract 0.17 from both sides. So now we have r minus 0.17 equals, and we have 0.44 log of n. Okay, now this means 0.44 times log of n. So technically this is being multiplied by the log of n. So to undo multiplication, if we want to get rid of 0.44 from this side, how do we undo multiplication? We're going to divide. So now what we're going to do is divide by 0.44. Okay, so it kind of starts looking ugly here. Okay, so we have r minus 0.17 over 0.44, and this equals the log of n. Okay. Now I'm going to take this equation and I'm going to rewrite it up here. Now, what I'm going to do, since these are equal, I can actually put log of n on the left side, right? Can I just switch those? If I have x equals 2 and the same thing as 2 equals x. Okay, so I'm just going to rewrite this as log of n equals, and we have r minus 0.17 over 0.44. Okay. All right, so I need n by itself, which means I need to somehow get rid of that log, and no, you can't just divide both sides by the word log. Doesn't work that way, okay? So what we're gonna do at this point is we're gonna take this log equation and we are going to rewrite as an exponential. So we did that earlier. It was just not quite as ugly as this. Okay, so let's think through this. Log is always base what? 10. So do you remember when we were rewriting, I said, okay, we're going to take this and we're going to go counterclockwise, and that would be how we would rewrite it exponentially. So here's what gets kind of ugly in this. So we have base 10. So we have 10 raised to, all of this is now your exponent. So r minus 0.17 over 0.44, that is the exponent to the 10. And that will equal n. And then that's all we're going to do with it. And then we're done. Whoops. Okay. That's the fun and algebra part that we get into just a little bit. Okay. So we'll go through this extra practice, kind of go through it pretty quickly. And then this assignment I've already scheduled and it will be due Friday. Okay. All right. So here we go back to our earthquakes. So our earthquakes go back to this Richter scale, which we know is base 10, right? Okay. So if one earthquake measures 4.3 on the Richter scale and another measures 6.5 on the Richter scale, how do the two earthquakes compare? So we've got 4.3, which would be somewhere around here. And what was it? 6.5. So now we're getting into moderate. So we went from minor to moderate. We know the larger the Richter scale, the more powerful it is. So when we're given two Richter scales, what do we do with these two Richter scale readings? We subtract them. So I'm gonna take 6.5 minus 4.3, and I get 2.2. Now, we know the 6.5 quake is the more powerful. So what we're doing is trying to find out how much more powerful. So to find out how much more powerful or stronger, what do I do with that 2.2? It's the exponent to 10. So I'm gonna do 10 raised to the 2.2. And I'm gonna go out 3 decimal places, so 158.489. So this tells me that the 6.5 is that much stronger than the 4.3. So I would say something to the effect of the 6.5 earthquake is 158.489 stronger. Okay, the number of miles of roads cleared, so because M is my standalone variable, I know this is my function, is given by, so here's my equation, and I can see it's a log equation, where D is the depth of the snow in inches. So I know this is my variable. Okay, make a graph. Okay, so I know I'm gonna have to put that in my calculator, but before I do, I'm gonna go ahead and label my vertical and horizontal. So I went ahead, instead of writing it out, I just defined it within my given information. So M is number of miles. And then D is depth of the snow. And this is in inches. And then they tell me that they're talking about or setting the parameters of 2 to 15 inches of snow. So we're gonna go in and do our y1 equals, so we're gonna change out that equation and be sure your plot is off. And then you're gonna set your window with a min of 2 and a max of 15, and then you're gonna zoom 0. Catch up. Be sure and clear out that other equation. And don't forget, fraction is alpha y equals 1. That's how you get to the fraction. I'm gonna go to window and do 2 to 15. All right, anybody have any problems? Okay, so I'm gonna sketch that. All right, express using functional notation the number of miles of road cleared if the snow is 10 inches deep. Given variable value variable is D equals 10, so we need to write that in functional notation, and then find the value. So what's my functional notation? M at 10. And that is 25 minus 27.25 times the log of 10 over 12. I got 27.158. Does that confirm? Make sure I didn't make an error. And what is this 27.158? That's the number of miles that have been cleared. So it asked for this, and it asked for this. So those are the two things I would look for to make sure you had if this was a test question. All right, how deep is the snow if 30 miles of road are cleared? What's given? Function is M equals 30 miles. So then I know in my equation, I'm going to put it in place of the M. 30 equals 25 minus 27.25 log of D over 12. Here's my Y1. I'm going to enter my Y2. I'm going to leave the window alone and see if it will cooperate. And it does. So I'm going to go to Calc 5. And I get X equals 7.865. And Y equals 30. Okay, so what's my final answer? B equals 7.865 inches. Okay. All right, so that assignment done, due Friday. Chapter 4 done. The last two sections come from 6. So it's got some different concepts in it. So let's see how far we can get in 6.1. All right, so chapter 6 is rates of change. And so what we're going to be looking at is something that you may not encountered before or in this aspect of what we're going to be looking at, and it's velocity. Okay, so when you get in a car and you drive, you're going a particular distance and speed. Okay, so notice that it says here, speed is always a positive number that describes how fast you are going. Obviously, if you're on the highway, 70 miles an hour, you have it set on cruise control, that's your speed, right? Okay, so what we're going to now talk about is velocity. Velocity does indicate speed. So part of what velocity does indicate is your speed, but it also is directional, okay? So we now have to consider not just the speed, but the direction when we talk about velocity. So here's what's new. Your velocity can be positive, and this is when you were moving away. So like if you're starting at this point and you're moving away from somewhere, your velocity is going positive direction. So the directional value would be positive. So that would be like positive 7, like if my starting point was Enid and I'm driving to Stillwater, I'm going away, so that would be positive 70 if we're talking about velocity, not just my speed, but also the direction. All right, but the key is with velocity, you can also have a negative velocity. So when I'm in Stillwater coming back to Enid, so then I'm in Stillwater and I'm driving back to Enid. So I'm still driving 70 miles an hour, but directionally I'm going in the opposite direction. So it's considered negative. Okay, so that is something that is different with the velocity. All right, so in this example 1, you'll see that we have 2 graphs. We're going to do one graph that deals with distance and one graph that deals with time, okay? So disregard this one for right now. We're going to look at this first one. And what we're going to do is we're going to create a graph that is giving us our distance versus or relate in relation to time, okay? All right, so when you're in the very corner, that's where you're starting from, like your driveway, okay? So let's say that we are at home. So this says, suppose you drive at a constant 60 miles per hour for 4 hours without stopping or changing direction. Okay, so think of a T-table. We can create a T-table or ordered pair, which indicates how long I've been driving, how far I've been driving, okay? So when I get in my car at home, I have not yet driven any time-wise. I haven't yet gone anywhere. So we always start at 0, 0, okay? So that would be this point right here in the corner. Now, the key is we've got 4 hours. So we have 1, 2, 3, 4 hours because our T is dealing with hours here, okay? All right, well, if we're driving 60 miles per hour, then at 1 hour, how far have we gone?
60 miles.
60 miles. So I would go, I'm going to do this as just, this is my 1. Here would be 2. So I'm going I'm skipping 1 just to make it easier to read. And let's see, what do I do here? I did. So let's say this is 60, 120, 180, and then 240. So this is my D, which is distance. And this is T, which is my time in hours. All right, so we started at home, 0, 0. In the first hour, we went a distance of 60. So I can graph that ordered pair. So I continue driving another hour. So now how far from home am I? 120, right? So each time you're just going to add 60 because we've got that cruise set. We're not stopping. We don't have to stop and go to the bathroom. We don't have to stop and get gas. And so each time you're going to add 60 because it's a constant rate of speed. So then my second ordered pair, or third one actually, would be 2 hours. And we have gone 120 miles. 3 hours, we've gone 180. And then 4 hours, 240. So this is a graph that is graphing the relationship of distance with time. Okay, distance with time. How many hours we've driven, now how far we are. Okay, now velocity is when it gets different. Notice this is still your x-axis, and this is your y-axis. So you'll notice that the x-axis is here in the middle. So because velocity can be positive, which would be above the x-axis, and below the x-axis is negative. This is when you're driving away from home. This would be if you went back home, okay? Now, here's the thing. We're still doing time, but now we're doing it in relationship to velocity. So this graph is going to be our velocity in relationship to time. So now my y-axis is my velocity, which is miles per hour. So it deals with not only my speed, but also am I driving away from home or towards home, okay? And then my x-axis is still t, which is hours. Okay, so now we're not talking about distance. We're not talking about how far away from home. We're only talking about the speed of my vehicle. Okay, so when I first get in the car, how fast is my car going? 0, okay? At 1 hour, not my distance, but how fast is my vehicle moving? 60 miles per hour, right? This is 60 miles per hour. Okay, at hour 2, how fast is my vehicle moving? 60. I'm not going 120 miles an hour, right? It doesn't increase like distance. I'm still going 60 miles per hour. What about hour 3 and 4? Still 60 miles per hour. Now, directionally, am I driving away from home or towards home? All of these are driving away from home, all right? So when I get in the car, I am driving away from my starting point, which I called home. So when I graph this, since I never turned around and went back, not only is my speed continually 60, but it's always going to be positive 60 because I am moving away. Okay, so I'm going to label this. Here's my 60 miles per hour, right? And then here is where we started at home. And then here's 1 hour, 2 hours, 3 hours, and 4 hours. And the key to remember is this graph is graphing my speed, not my distance. So I get in my car, I get on the highway, and I speed up and I hit 60, and then I am on cruise control that whole time. Because here's my ordered pair: 160, 260, 360, 460, because my speed basically was on cruise control. Okay. So the key is, one is distance, one is only your speed, right? So we know that away from home, my speed is up here. If I was going towards home, it would jump down here negative. Well, I'll get into that in a minute. Okay, I was gonna say something and I was like, that may not be helpful. All right, so again, we're gonna do first our distance in relationship to time. So we'll do that first. Okay, suppose you drive 60 miles per hour for 1 hour. Okay, so I'm gonna go ahead. To me, it's easiest to figure out my ordered pairs. And always when I get in the car, no time has passed, I haven't gone anywhere, okay? All right, so 60 miles per hour for 1 hour. So I've driven 1 hour, how far have I gone? 60 miles an hour, okay. So then the next hour, I'm going 50 miles per hour. So in hour 2, am I gonna put 120? No, because I've only gone 50 miles during this hour, right? So then what I'm gonna do is add the 50, and now I'm at 110. All right, so then I stop and rest for an hour. Okay, so an hour time has passed. I was resting. How far did I travel? 0, so I'm still how far from home? 110 miles. And then, what color have I not used? Green. And then I drive 70 miles per hour for the last hour. So now I'm going to add 70, so I end up at 180. Okay, so how does that look on my graph? Well, here is T, my hours. And then, of course, this is D, my distance. And I'm gonna label it the same, 60, 120, 180. That was weird. 240. And here I have 1, 2, 3, 4, and we start at home. Okay, so my first order pair is over 1 up 60. So here is what that would look like. And then at 2, I'm not at 120, I'm at 110. So here would be 90, so would be about right here. But still increasing, it is not increasing quite as fast. It looks like it on my graph because I can't be super exact. And then for the next hour, I haven't moved. What is my speed during this time? 0. I'm not moving, I'm resting. Right? Okay, just thinking when we get to velocity. And then the fourth, we go to 180 because we went, oh, I need to make up time. And so this is a little bit sharper increase. So here was the first, so that was in that color. And then this was the second one that I did in orange. And then I went what? Purple. And then green. So that's the relationship to the information up above. Okay, so that's distance. Now we still are 180 miles from home. All right, so now we're going to look at this with velocity. So now when we're graphing velocity in time, what we are concerned with is the speed of my vehicle and which direction. Am I going away from my starting point or back to? All right, so we had time, which we know we dealt with 0, 1, 2, 3, 4. And then our velocity, which is our miles per hour. Okay, so we start out at 0, 0. All right, how fast am I driving in that first hour? 60. In that second hour, how fast am I driving? 50. In that third hour, how fast am I driving? 0. And then that last hour, 70. All right, now what about directionally? Am I always going away from my home or starting point, or at any time did I go back towards? I'm going away, so I'm going away, so that means everything will be positive or above the x-axis. So we haven't even dealt with what happens when it comes down here. All right, so again, this is our t, which is hours, which we have 1, 2, 3, 4. And this is velocity, which is our miles per hour. And so here's 60. And then we went 120. Okay, so here's where I start. And ultimately, during this hour, I was driving 60 miles an hour, right? So I sped my vehicle up, and for this hour, I drove 60 miles an hour. And then in that second hour, I slowed down and went 50 miles an hour. And then I stopped and rest. Where do you think we'll go on the graph at 0 miles per hour? Based on the axis. So right here, just chilling and resting. And then bam, I go, oh crud, I'm gonna be late. I need to speed up. And in that last hour, I went 70 miles an hour. So this represents 60 miles an hour, 50 miles an hour, 0 miles an hour, 70 miles an hour. Okay, and again, all of these are going away. We are getting ready to do another example, which is going to change things for us a little bit. All right. So again, this is going to be distance and time. And this one is going to be velocity versus time. So I know this is D, which is distance. And this is T, and I don't know yet if I'm talking hours, minutes, or whatnot, so I'm gonna read it now. Okay, suppose you leave home, so right here is home. Traveling west at a constant 60 miles an hour for 2 hours. Okay, let's deal with this first. So here's my 1, 2, 3, 4, and I don't know how many hours I'm going. This is still gonna be 60, 120, 180, 240. Okay, so time and distance, I'm at home. Okay, so for 2 hours, I go 60 miles an hour, okay? So how far have I driven in that first hour? 60 miles. And I stay at that constant speed, so I add an additional 60 miles. So I'm gonna add an additional 60 miles, so now I'm at 120. Okay, so I'm gonna go ahead and graph those. Here's 160 to 120. And it looks like that. Okay, all right, so let's see what happens next. At which time you reach your destination, so we're there, and you stay there for 1 hour. So we're at our destination and we stay there for 1 hour. Okay, now this graph is distance. So another hour has passed. How far am I from home? I'm still 120 miles from home, right? So here's 3. There is hanging out at my destination. Okay, all right, then it says you drive back home at 60 miles per hour again. Okay, so I'm still going 60 miles an hour. But here's what you've got to be careful of. Where am I headed? I'm headed back home, right? So am I going to add 60 miles to this? No, that would put me 180 miles from home. So we're still going 60, but now we're getting closer to home. So I'm going to subtract 60. So then I am 60 miles from home, drive another hour, and now I am back home. So that would look like, so 465.0. So notice now my distance is increasing because I'm driving away from home. My distance stays the same because I hang out for an hour. And now my distance is decreasing because I'm going back home. Okay, all right, so that means my velocity graph is going to look different this time. So we know that this is miles per hour. And this is T, which is hours. Okay, so we have time. And now we have velocity, which is miles per hour, and we know that is always at 0, 0. Okay, so I'm gonna look over here or up here, it doesn't matter. So in those first 2 hours, how fast were we driving? 60 in both of those, right? Now, at that point in the 3rd hour where I'm hanging out right here, how fast am I driving? 0 miles an hour. Now, here's the key here, because now I'm going back home. Now, how fast am I driving still? I'm driving 60 miles an hour, but what happens here? This right here, I was driving away from home, so we had positive velocity. I'm still driving 60 miles an hour, but now I'm driving towards home, so that tells me that which direction does this become? Negative. So these are negative 60. Not that you're driving negative 60 miles an hour, because we're not. We're still driving 60 miles an hour. The negative tells me which direction we're going. Okay, so what will that look like on a velocity graph then? Here's 1, 2, 3, 4, and 5. Okay, so I start at home, I go away, and I'm doing this for 2 hours. Because here's 160, here's 260. So then when I am at 0 miles per hour, where do I go on the graph? On the axis. I stop and then I'm on the axis here. And now 4 and 5, I'm still going 60 miles an hour, but I have to show that I'm going back home. So now it will go below the graph here. Whoops, that should be on that line here. Now, notice that in relationship to my original graph. When this is increasing, you're above the line. When this is constant, you're on the axis. When this is decreasing, you're below the line. Okay? And these bullet points are just reiterating that. So velocity is rate of change directed, meaning positive or negative. When velocity is constant, the distance is sloped and the velocity graph is horizontal. So that just goes through what we did here, mainly these 3 points. Distance is increasing, velocity is positive. Distance is decreasing, velocity is negative. Distance is not changing, here velocity is 0. Okay. All right, let's get through this example 4, and then we'll call it a day. Okay, so notice here is your distance graph and here is your velocity graph. Okay. Okay. An airplane leaves Kennedy Airport in New York and flies to Miami, where it is serviced and receives new passengers before returning back to New York. Assume that the trip is uneventful and that after each takeoff, the airplane accelerates its standard cruising speed, which it maintains until it decelerates prior to landing. Make graphs of distance south of New York versus time and velocity. Okay, so they don't give us like 1 hour, 2 hour. We're not going to get exact distance. We just want a visual of what's going on. Okay, so we're starting where? We're starting in New York. Okay, so right here, we're in New York. So what's going to happen with the plane? You're going to take off and you're headed towards where? Miami, right? So we're going towards Miami. So we're going away from New York. So what should our graph be doing as far as distance?
Increasing.
Increasing, right? So what I'm gonna show is the plane takes off. It increases because I'm going away from New York. All right, and then it says we reach Miami, and then what happens? Do they immediately return to New York? What are they gonna do? Have to service the plane and get new passengers. So what happens to the distance away from New York? It stays the same, doesn't it? So however far this is, when I'm sitting in the airport, it's getting serviced and new passengers, I'm still that same distance from New York. So however much time passes, and then what is that plane gonna do? It goes back to New York, so now what is my graph gonna do? Decrease. Okay, so this gives us an idea of my velocity then. So I'm gonna try to get them both in here. Okay, so again, I don't have numbers. I do know this is New York. And I do know that above is when we are going away from New York. And below is when we're going back towards New York. So as the distance increases in relationship, am I above or below? Above, because I am going away. So whatever speed that plane is flying at, it takes off and hits that speed and stays that speed. And then it reaches Miami. It's getting serviced and new passengers. What's the speed doing? 0. So they landed. And then they got the plane serviced and new passengers. And now they're going back to New York. So where does the graph go with velocity? Whoops, I went a little far, but that's okay. All right. So one deals with speed, one deals with distance. Okay, so we are going to stop there. Let me see exactly what we need to